What's up, guys? My name is Josh, and welcome back to FAB 201, episode number 4. Today we're going to be going over perhaps the most dreaded subject for a lot of people growing up, mathematics. And we're going to be talking about how to use math for a competitive advantage in Flesh and Blood using real-world examples. Next week we're going to be talking about how to brew Everfest, and this will be probably after the first ProQuest weekend, so we'll probably have some deck lists to look at, and we'll be looking at the top cards from that set and analyzing any new strategies or tactics that have come up over that weekend. But that's for next time. Let's just jump into today's topic. So, how do we use math for a competitive advantage? Well, math can help us in several different ways. It can help us build better decks. Bringing a better deck to a competition is obviously going to be an advantage. It can also help us make better decisions when sideboarding and playing out our turns in the actual game. So there is a balance between consistency and risk. If you always want to have a blue in your hand, you could run 60 blue cards. You would have a very, very consistent deck, but it would be pretty bad because you're running 60 blues. All right. So there has to be a balance between the consistency of the deck and how much risk you're willing to take at the same time. So I like to use a rule of thumb. Now this is just something that I've developed over the course of playing many games of FAB. And this is how I like to categorize things. I want to be 80% certain of an outcome if when I fail, in the case of, let's say I fail to draw a blue, I fail to draw a combo piece, whatever, that it is not that bad. Okay, so that example of this is I have the tempo in a classic constructed match, and then I failed to draw a blue card, so my follow-up turn is not that great, and we're playing like a mid-range mirror. That's fine. That's not so bad, okay? However, I like to be 90% certain of things when failing would result in a disastrous result. Okay, so for example, if I'm playing Reinhardt, this is why we run Gambler's Gloves. Okay, so that if we roll a 1, at least there's a good chance that we don't roll 2 1s in a row. All right? So those are just 2 examples. So today we're going to be using something called the Hypergeometric probability calculator. There is a good chance that you have heard about this if you have been in the TCG area for quite a while. This is an excellent tool for helping build better decks and helping you make better decisions. So let's you could also use Excel and Google, but I'm going to guess that most of you are just going to use the calculator because it's much easier. All right. So let's just jump into an example. We're going to be going through 4 examples today, and they're all going to illustrate something a little bit different. But let's start off with the most basic example. All right. Let's say you're playing as Viserai, and one of the best cards that you could play, assuming that you go first, is Read the Runes. Whether you're playing as a tempo or you're playing as an OTK, starting off with this card is really good. So what is the chance that you have Read the Runes in your opening hand, assuming that you run 3 red, 3 yellow, and you have a 60 card deck? Now there are some fringe cases. There's also Oath of the Arknight, but we're not going to consider that here. Obviously that can most of the time that could act as copies 7 through 9, but we're not going to look at that. All right. So in your head, what do you think like, based on your experience, what do you estimate this probability to be? Well, let's take a look. So we're going to use this calculator. If you go to Google and type in Hypergeometric calculator, this is the first result. This is what I use all the time to do quick calculations here. So let's run through how to use this. All right. Population size, in this case, represents your deck, how large your deck is. So in this case, there's 60 cards. Number of successes in the population, this is the cards that you want to hit. So in this case, this is the 3 copies of red read the runes and 3 copies of yellow read the runes. So we have 6 successes in the population. Sample size is 4 because we're going to draw 4 cards at the beginning of the game. The number of successes in the population is 1. We just need 1 and we'll be happy. All right. And so then it'll spit out several, it'll give us the hypergeometric probability for x equals 1. But generally that is not so useful unless we're using it in combination with other things. In this case, we're looking for the cumulative probability. So we're saying the chance to draw at least 1. And in this case, we can see that it is 0.35, which we can convert to a percentage, and that becomes 35% basically. So we have a 35% chance to have at least 1 copy of Read the Runes in our opening hand. Not bad, especially when you consider that Oath of the Arcanite acts as copy 7 through 9 most of the time. So how can we apply this in game? Well, we shouldn't let Viserai go first. If you're playing against Viserai, you want to be going first. All right? And the math here tells us why. All right? So the calculator is great and all, but it's much easier to just have just remember these key percentages here. In Classic Constructed, if you have a 3 of, you're 20% chance to see that in your opening hand. If you have a 6 of, you're 35% chances to see it. And if you have a 9 of, then you're 50% chance to see it. Now this also applies to the following hands as well, assuming that you've had a fairly normal distribution of cards, all right? So in Blitz, the most common 2 of is Sigil of Solace. So in 20% of games, you'll have that in your opening hand, and you'll be starting the game on effectively 23, which is quite nice. All right. Another example here is in Blitz, if the Ira goes first, let's say I'm playing Dorinthia against Ira, and the Arsenal card, unless they're playing very, very offensively, there's a good chance half the time that is a defense reaction in Arsenal, assuming that they run just the standard 3 copies or 6 copies of Flick Flack. All right. So let's move on to the second example. All right. In example 2, we're going to be looking at my Dorinthia deck in Blitz. So in my Dorinthia deck in Blitz, I run 21 reds, 5 yellows, and 14 blue cards. All right. And in order to have an effective turn as Dorinthia, you generally need a blue. So what is the chance that we have a blue? Well, it's very easy to calculate that. We could put our population size as 40, not 60, because we're looking at Blitz. We have 14 blues, so those are considered successes. The sample size is 4 because we draw 4 cards, and number of successes is 1. And we're looking again at the bottom, the cumulative probability, 83% chance to have at least 1. And you remember how I was talking about my rule of thumb, 80% is generally what I'm shooting for in terms of consistency. One thing to note is that going from 80 to 90% consistency generally involves, to get from 80 to 90 and 90 to close to 100 obviously takes an exponential amount of commitment to something. All right. So let's break this down a little bit. So why do I use 21, 5, 14 as my ratio? Well, we need to look at what is considered a good or bad hand. All right, so X in this case represents the amount of blues that I have in my hand. All right, we'll come back to X equals 0, okay? X equals 1, 2, 3, 4. These are very straightforward to calculate. You just put them into the calculator and you look for the hypergeometric distribution. And as you can see, the chance of having 1 blue is about 40%. The chance of having 2 blues is 32%. Chance of having 3 blues, which I would consider a bad hand, is 10%. And the chance that you drew 4 blues is 1%. Now, in the case of X equals 0, so we're saying if we did not draw a blue, there are 2 ways that can occur in. The first way that could occur in is we draw 4 reds. Okay? And then, so what we can do is we can put 40 into the population size, 21 into the successes, 4 into the sample size, and 4 into the successes. And we can calculate that that is about a 6.5% chance to draw 4 reds. All right? Then we can take the probability to not have a blue minus the probability of having 4 reds, and then we can create the final situation where we do not have a blue, but we have at least 1 yellow, which occurs 9.9% of the time. All right? So we can add up the bad outcomes, which is drawing 4 reds, that's bad, plus drawing 3 blues, 10.3%, plus drawing 4 blues, 1.1%, and we get 17.9%. And then we can add up the other ones where we can do 100 minus 17.9, whatever. And in this case, so we can see that roughly we have an 82% chance of having a good hand. Now, what determines what a good hand is? That's going to vary from deck to deck. And in fact, we're going to look at this a little bit more in depth in example number 4, where we use multivariate distribution, which is we'll cross that bridge when we cross that bridge. All right, let's look at example number 3. I often get asked, why do I not play 2 energy potions and a time snap potion, or 2 time snap potions and an energy potion? Well, the reason is that going from 2 to 3 potions actually create. So if you think about a situation in game that is disastrous, as Dorinthia, a disastrous situation is when you draw 2 potions at the same time, other than turn 1, which is actually okay. If you draw 2 potions, then you can pitch 1, but you're still having to hold 1, and unless you have unconditional go again, it's not really where you want to be. So let's break it down by using math here. So on the left here, we can see that given that we run just 2 potions, the chance that we draw 2 potions on a 4-card hand is 0.007, which is less than 1%. And in other words, we could go 1 divided by that, and that gives us 130. So another way to look at it is 1 in 130 hands, you will draw both potions together if you run 2 of them. All right, but let's see what happens when we run 3 potions. Okay, so we run the same calculation here, and we get 0.02, which, in other words, means 1 in 45 hands you will draw 2 potions together. Okay, we can look at a 10-turn game and calculate that if we run 2 potions, the chance that we run into a situation where we draw 2 potions at the same time is only 7%. In other words, we have 93% chance to avoid this. However, with three potions, there's only an 80% chance that we don't run into the disastrous situation. All right. And that is too high of a chance. There's basically a 20% chance in a turn-turn game to just lose. A lot of tempo, or if it's a critical turn where you have to block, it could just be a disaster. Okay. So we really, really want to avoid that. And remember what I said is I want 90% consistency on things that matter. And in this is an example of something that matters, right? All right. So let's look at example number 4. So before all this, we were looking at mutually exclusive categories. We were looking at blue or not blue, read the runes or not read the runes. Okay? So in order to analyze situations where you have more than 2 categories, you have to use something called multivariate hypergeometric distribution, which is basically the advanced form of what we just learned. All right. So let's look at a average Dorinthia hand and calculate how often do you have a good attacking hand. So what defines a good attacking hand in Dorinthia? Well, I generally consider it to be 3 things. It has to have some sort of threat. So in this case, I would consider Red Warrior's Valor, Spoils of War, and Steelblade Supremacy as threats. And you have to have a pump. So Stroke of Foresight, Out for Blood, Iron Song Response, Overpower, Route, Biting Blades, Singing Steelblade, etc. Right? And you have to have a blue pitch. Okay? So if you have at least 1 threat, at least 1 pump, and at least 1 blue, you have a good attacking hand. So in my blitz deck, the ratios come out to this. I have 13 good pump spells. I have 6 good threat spells. I have 14 blue pitch cards, and I have 7 other cards. These are things like Sigil, Sink Below, cards that aren't threatening and aren't a pump, like Sharpened Steel, or very, very situational cards such as Twinning Blade or Shatter. All right. So we can, again, use a calculator to figure out what is the chance that we have a good attacking hand. You can go to this website, deculator.appspot.com, and you can put the values in, and it'll spit out the probability for you. Alternatively, you could calculate this in Excel, but this is much, much harder to do than this is beyond the wheelhouse of most people. So using the calculator, we can put our 4 categories in. We have threat, pump, blue pitch, and other. We have 6, 13, 14, and 7 copies of those cards respectively. And we want 1 copy of 1 threat, 1 pump, 1 blue pitch in our hand. And we're going to draw 4 cards. And we can see that the probability that we draw what I consider a good hand is 26.3%. Now, anybody that's played Dorinthia long enough knows that this is about correct. And this is one of the reasons why I consider Dorinthia to be a mid-range deck and not an aggro deck. As an aggro deck, you need to consistently attack and maintain tempo, and you can't brick on your attacks. This, given that 75% of the time you're not going to have a good attacking hand, means that you're going to have to play defense, you're going to have to set up turns, you're going to have to block a bit, attack back lightly, and wait until you draw the good hand, and then you can go. So yeah, let's look at some key takeaways now. So using math will help you brew better decks. In other words, more consistent decks that don't sacrifice power for consistency. There's obviously, like at the beginning of the video, I talked about if you really want a consistent deck, you play 60 blues. Obviously, that is not optimal, though, right? Remember how I talked about there are 2 levels of consistency that I want. A 80% consistent, 80% consistency for decisions or outcomes that I don't really, if things go wrong, that's fine, no problem. However, I really want 90% consistency for important or pivotal moments where failing would be disastrous. And I think that's just a good rule of thumb for you guys to consider as well. Using math will help you make better decisions in sideboarding and during the game. However, this is not the be-all end-all of things. In order to use the techniques that I talked about in this video, you need a good understanding of the game, of its mechanics and concepts, and each hero is a little bit different. For example, determining what a good hand as Dorinthia is may vary from person to person, and it takes a lot of experience with the deck to get to a point where you could say, okay, I consider this to be a good hand, right? And just using math by itself is not going to get you very far. You have to combine it with game knowledge, and even intuition would also help as well. A lot of times what you feel in your gut is if you've played enough, your gut feeling will generally line up with the math, which is nice when you go back and check things out. So yeah, I guess that summarizes everything that I wanted to talk about. In this video, we used a lot of Dorinthia examples. However, you can easily apply this to many different heroes, and I hope that you use the Hypergeometric calculator and the Multivariate Hypergeometric calculator to improve your brewing, your sideboarding, and your strategy and tactics in game. So yeah, I hope you're doing well. Thanks for watching. See ya.